In this video, we're going to look at some examples of using Laplace transforms to solve second-order linear constant coefficient differential equations. So nothing new in this video, just working out some examples and using what we've learned in previous classes and videos. In the first case, I want to show one that is over-damped if it came from a mass on a spring. So in other words, the left-hand side here is going to be something that whose roots, the corresponding quadratic has two real roots. In other words, it can be factored. And that plays out sort of algebraically in a certain way that is different than the case when it doesn't factor. So I want to start with a case like this. Okay, so let's give it a try. We have, as I say, second order constant coefficient. We have a damping term, and of course just the spring constant. And then our forcing term on the right is a negative exponential, so a decaying force that doesn't turn on until time t equals 2. So at time t equals 2, it's basically e to the minus t shifted over to 2, and before that it's 0. We have initial conditions as well. All right, so Laplace transform both sides. On the left-hand side, we would get this. So you see second derivative of the Laplace transform is here. I'm plugging in the initial condition, -1. That there's two negatives here to make a plus 1s, and then a 2 is a minus 2. Okay. Now on the right-hand side, the Laplace transform of that is a job for the t-shift rule. And just to remind you what the t-shift rule says, here it is, that the Laplace transform of, well, exactly what we have, right? V8's no problem, but we have a heaviside function times a shifted function, and the heaviside function turns on exactly the amount that the function gets shifted by. In other words, the a here is the same a here. And that's what we have, right? We have a 2 here and a 2 here. And the rule says that the result would just be, so e to the minus 2s times, and then what we do is we use the Laplace transform of the y, non-shifted, before it was shifted. So before this was shifted, this is just e to the minus t, right? It was then shifted over, but before that it was just e to the minus t, and the Laplace transform of e to the minus t is 1 over s plus 1. As shown. And I don't want to forget there was also just a constant multiple of 8 that I need to throw in there as well. Okay, so this is the algebraic equation we get after taking the Laplace transform. Now for the purposes of this video, I'm not going to talk through all the algebra, so I know this is algebra that you can do. Feel free to pause the video at any point if you want to just take a second to see the different algebra steps that I'm showing. But of course the next thing to do would be sort of work out this left-hand side, and we would get something that looks like this. So I've collected all the capital Y of S terms, and now I'm going to move these non-Y of S terms over to the other side, and then I'm going to divide by this quadratic to solve for Y of S, and that will result in this expression for capital Y of S. And so our next step is going to be to take the inverse Laplace transform, but we have two fractions that are kind of a mess and not really ready to have their inverse Laplace transforms identified, so we do want to do some partial fractions. Okay, so for the first term, the first fraction, I feed it into a Wolfram Alpha or a calculator, and the partial fractions that I get, and remember that we said that this quadratic factors, so that really will break down into two separate linear pieces that can then be separated into two separate fractions, and we will get that. And now we're going to do the second one. Now for the second one, it has an e to the minus 2s. Just move that to the side. when you go to do your partial fractions, don't include that in the partial fractions. There's no need to. In fact, I can just simply do a plus e to the minus 2s, and then I'll put the result of the partial fractions inside here. I'll include the 8 in my partial fractions calculation that I give my calculator. Might as well. And when I do that, I get this expression. Okay, so that is the full capital Y, that is the full Laplace transform, and now I think I am ready to take inverse Laplace transforms. Notice that other than the constants, we have lots of constants to track, but the key terms are all 1 over linears, and so inverse Laplace transforms of all those will give us exponentials. And it's just that for these guys, there's going to be an exponential multiplied on there, and I'll talk about that in a second, how we deal with that. Okay, but let's see. We would get, for example, for the 1 over s plus 7, that is the Laplace transform of e to the minus 7t, and we'd have minus 5/4, and the 1 over s plus 3 term gives me an e to the minus 3t. Okay. To take the inverse Laplace transform of the term that has the exponentials, we remember, again, the shift rule that says that if you have an exponential times something that is a known Laplace transform, you want to go back, you get this. So we're going to get a UA, we're going to get a heaviside function. For us, the A is 2. So we're going to get a U2 of t. And then for each of these, and by the way, the U2 of t is going to be on each one of these terms, because the e to the minus 2s is on each one of these terms. So maybe I'll just keep the same sort of factored out version. The e to the minus 2s turns into that. Yeah, and then what we want to do is figure out what the inverse Laplace transform of each of these guys is, but remember that it should also be shifted by, in this case, 2. So we would have a negative, and then for 1 over s plus 3, right, that normally would be e to the minus 3t, but it should be shifted by 2. So instead of t, I should have t minus 2. Continuing, I would have plus 1/3. And then the 1 over s plus 7 right here, right, normally that would be an e to the minus 7t. But again, the presence of this guy on the outside means not only this, but also that each of these guys is shifted by 2. And so finally then we have plus 2/3. And again, 1 over s plus 1 would be e to the minus t, but it should be shifted minus 2. Okay, and so this is our final answer. And just a reminder how to interpret this, how to read this with this heaviside function in there. For the first 2 units of time, it's just this, because this is 0, right? It's just these 2 exponentials added together. But then after 2, this is really a 1, so it's this and this together. They're combined. So again, for the first 2 seconds, it's this, and then it's the whole thing after 2. Okay, we're going to move to a second example now. And in this case, it's going to be an underdamped case, and you're going to see that the quadratic that we end up dividing by, does not factor. And that's really going to affect how the partial fractions and then inverse Laplace transform phase goes. So we'll have to pay close attention when we get to that point. That'll be something we haven't really seen yet. Okay, but let's get started. It starts out the same way. We take the Laplace transform of both sides of this. Here is the Laplace transform of the left side. So again, second derivative right here, plugging in the initial conditions in the appropriate spots. First derivatives Laplace transform right there with the 2 in front, and then plus 2 times the Laplace transform, just plain old capital Y. On the right-hand side, what we have here is, again, sort of a shifted and turned on version of just the function t. Right? This is the function t, except it's been shifted to the right by 1, and it doesn't turn on until 1. So our shift rule tells us that we just take the Laplace transform of t, which, if that's all it was, would be 1 over s squared. But the heaviside function and the shifting part together, the way that affects the Laplace transform is with an exponential factor, an e to the minus s, minus 1s. So that minus, it's always a minus, but the 1 is coming from the 1 here and the shifting to the right by 1 there. And so that would be the Laplace transform. Okay, so again, that would be the t-shift rule. All right, now a little bit of rearranging, and again, I'll just jump to the result, and you can pause and look at the algebra more carefully if you choose. We get something that looks like that after rearrangement, and now I'm just going to bring everything over to the other side, solving for capital Y, and that will look like this. Okay, now we then normally would go to partial fractions. And this is where it's going to start to be different. If you put this into a partial fraction, if you do partial fractions on this either manually or using a calculator or Wolfram Alpha, you're going to find that it can't do anything with it. It'll just give it back to you. And the reason is that the bottom doesn't factor into two linear factors. This isn't this as promised, this quadratic does not factor, so there's no way to break it up. Well, okay, so we have seen cases like that before, except the times we have seen it before, there was no s term. It was just an s squared and a constant. This 2s is the new part. If this 2s wasn't here, if I just took that out temporarily, okay, then we wouldn't need partial fractions, and we wouldn't need, we could just do the inverse Laplace transform, because the s squared plus 2 part, right, that looks a lot like our Laplace transform for cosine or sine, s squared plus omega squared. And maybe this part would correspond to a cosine, and just the constant one would correspond to a sine, and we could work that out. Looks like omega would be a square root of 2, and we would work that out. Okay. But what do we do when we do have this middle term? Okay, well, anytime in math when you have a quadratic and you know what to do if you don't have the middle term, but you do have it, the solution is completing the square. We complete the square. So I am going to rewrite the denominator here. Let me just rewrite the top. So we have to remember how to do this. So you go s squared plus 2s, and then to complete the square, right, we would need half of that 2 squared. Half of that 2 is 1. 1 squared is 1. So we need a plus 1. Well, we had a plus 2. Our constant term was a plus 2. So a plus 1 is what we need, and then I guess we just have a leftover plus 1. And then the whole idea is this part right here, right there, factors as a square. That will always be the case if you completed the square correctly. So if you don't mind, I'm just going to do this in place. That's s plus 1 quantity squared. Okay. And now, at least the bottom part, now we'll have to make the top part reconcile with this, but now it is like the denominator of the inverse of a Laplace transform of a sine or a cosine, only with a shift to the left by 1. So that's how we're going to get sines and cosines in here. Okay. And in fact, I'm going to, because we're going to have one of each. Again, the 3s will be one of them, and the 9 will be the other. Let me break this up into two pieces. Let me just make the 3s part, and then plus 9 over, and then we'll have the same denominator. Okay. If it's okay, let me keep going with those two terms and do the inverse Laplace transform just to complete this thought, and then we'll come back because we still have that whole other term to deal with. Okay, so I'm putting dot, dot, dot. We have to come back to that. Okay, so now this guy is going to be the easiest. Let me do that one first. In fact, that one is going to be exactly as it is. I don't have to do anything else with that. And when I go to my inverse Laplace transform and go back to little y, right? Now notice my omega squared is 1, so I need a 1 up here, and that will correspond to my sine rule. So again, if you look on your Laplace transform table, if I had a 1 up here, this would be perfect. Well, except for the shift. We'll deal with the shift in just a second. If I had a 1 up here, this would be the rule for sine of 1t. So I just move the 9 off to the side, and I leave a 1 there, and so I would have 9 sine of 1t. Now, the fact that it was shifted, though, means it's a job for my s shift rule. My Laplace transform, my s variable function, is shifted. And our s shift rule says that if you want to do a Laplace transform, just take the Laplace transform as if it weren't shifted. Well, I've done that. But then tack on an exponential, e to the at. For us, a is -1, right? So we would have an e to the minus t. And again, that is corresponding to that shift right there of s plus 1. Okay. So I hope you don't mind that I'm kind of taking one term at a time and just going all the way through to the end. All right, let's go back to this first term. So for this guy, this one, because we have an s on top, that looks a lot like cosine. And it is going to turn out to be a cosine. However, it's not quite ready for prime time yet because the instance of s down here is shifted to the left by 1, but this one is not. So it's like only half shifted, so to speak. That doesn't even make sense, but you know what I mean? Like only part of it has had the shift process applied to it. But it's okay because we can fix that. We can sort of insert and then take away at plus 1 on this top s. So here's what we're going to do. We're going to go 3, and I want it to be an s plus 1, because that's what I want it to be, right? But of course, I can't just do that for free. So in effect, because that was in parentheses with a 3 on the outside, I've added 3 that I shouldn't have, so I need to take that away. And then on the bottom, I have s plus 1 squared plus 1. Now what I'm going to do, and I apologize for this. So now this part that I've just highlighted, that part is working for me. And that combined with my denominator is going to turn out to be a cosine. But the price I had to pay to make it work is this extra minus 3. So if you don't mind, I'm going to take that minus 3, I'm going to make it its own term. So let me take it away there. And then minus 3 divided by, and then, yeah, s plus 1 squared plus 1. And so now, this term, I'm going to, and in just a second I'll do it, that's going to turn into a cosine, but with a shift rule applied. And this guy is actually, you notice, except for the 3, it's the same as this guy. And in fact, really, I could have, if I had dealt with this term first, I would have noticed this, and I would have had this term, and I could have combined them. You see I have a -3 and a +9. I would I would have made this a +6. These two terms together would just be a +6 over that denominator. So it'll end up being just +6, right? Those two terms, in other words, those two terms have the same inverse Laplace transform, and I'll just have -3 of the one and +9 of the other. I'll get +6 right there. Okay. Now back to this guy. Now it's ready for prime time. We have s+1 in place of s everywhere. So if it wasn't +1, if it wasn't shifted, right, we would just have 3, and we would have cosine of t. Again, cosine of 1t, because you can see the omega is 1. But then the shift, just like on this other guy, will introduce an e to the minus t. Minus t. There we go. Okay, so going back to this line, this guy was broken down further, and there's its inverse Laplace transform. Okay, now we're ready for this guy. Now, this one does have, and it already is, factored. The denominator can be factored, and it already is. We know this part of it can't be factored further, but the s squared part is factored out. So there is going to be something we can do with partial fractions. Now also remember that this whole guy will have an e to the minus s on the outside of it. So, whoops. We will have e to the minus s, and then just sort of put that on the side for the time being, and then 1 over this denominator. Now, so this will have some partial fractions decomposition that can happen. And when you do that, you get this. 4 terms. Just coincidentally, they all have coefficients of 1/2 in front. This last one has -1/2, but they're all 1/2. So actually, I could factor out that 1/2, and I will. And then you see I have 2 terms that have the quadratic in the denominator, and then 2 terms, one term that just has an s squared, and another term that has just an s in the denominator. Okay, so like I said, I can factor out the 1/2. And I already have the e to the minus s factored out. And again, for these two guys, the denominator can't be factored further. So this is as far as it goes in terms of partial fractions. And again, it's the same as before. We have this plus 2s, and so it's completing the square idea. So let's see. So we'll have, for that first one, it'll be s over, and we already know how this works because we did it, s plus 1 squared plus 1. Okay, the second one will be plus 1 over s plus 1 squared plus 1. And then I'll just rewrite the others, minus 1 over s squared, plus 1 over s squared, and then minus 1 over s. Okay. All right. Now, once again, here, this guy is going to present a problem because it looks like it's going to be a cosine. It wants to be a cosine because we have s on top and, you know, something squared plus omega squared down here. But it's not matching. We have s plus 1. We have this guy being shifted, but this guy is not shifted yet. So I need to make it match. So I'll insert a plus 1. Now I can't do that for free, so I'll take it away. Okay. And then again, what I'll do is I'll split this up into 2 fractions. The s plus 1 over the denominator, and then the minus 1, I'll separate that as its own fraction. So that'll look like this. Okay. And I'm really lucky in this case because notice now that guy and that guy, not only do they combine, they cancel. So these two are completely going to go away. And so I guess I'm doing this in place. The final document will be hard to read, but if you're watching the video, this will make sense. I'm going to just delete those. Okay? Yeah. And so let's see. Let's see if we can figure out the inverse Laplace transform now of all of this. Okay. Hang on to your hat here because here we get to use both shift rules. So let me step you through this. For this guy. All right, remember, if there was no plus one here, if it wasn't shifted, we would have simply a cosine of 1t. Again, the omega is 1 here, right? So we would have that. But it is shifted to the left by 1, right? So like really minus a negative 1. And our S-shift rule says that the effect of that will be to just introduce an exponential on the outside of your inverse Laplace transform. So e to the minus t. Okay. So that right there would be the inverse Laplace transform just of this term. But then we also have times e to the minus s. So now we get to use the t-shift rule, which I have just inserted down here. And the t-shift rule says if on your Laplace transform side, if you have an exponential, the effect of that back in when you take the inverse is two things. First, a heaviside function, and also it gets shifted. Your inverse Laplace transform gets shifted. So those two things I will have, and it's e to the minus s. So we have an a of 1 here. So I'll have a u1 of t, and this gets shifted by 1 to the right. So that will mean t minus 1 here and t minus 1 there. Okay. So that right there is the inverse Laplace transform of, well, this term with the exponential. Oh, and I forgot the 1/2, or I almost forgot the 1/2. There we go. Okay. Now we still have this one and this one to do. They'll be a little bit easier. We won't have to use both shift rules for this one. So 1 over s squared on its own would be a t, right? That's the Laplace transform of t. But the e to the minus s, again, using the second shift rule, says that we have to insert a u1, and we have to shift the t. And again, I can't forget the 1/2 in the front of all this. And then finally, minus 1 over s, so minus. And let me put the 1/2 in so I don't forget it. 1 over s, it is that's the Laplace transform of just 1. But again, the e to the minus s out here means I have to insert a u sub 1 of t, and I have to shift my function, but my function is a 1. It doesn't have the variable in it anyway, so shifting it just gives me the same thing. And since it's times 1, I'll just delete it. Okay, wow. So there is the final answer. It got a little hairy there in the middle, and this had a lot of little tricks of the trade, and this is like the hardest one that we've seen and the hardest one that you will see. But there you go. So study this example, and if you can understand this one, you can do any of the ones that are thrown your way.